One of the things that I did was picked problems from the 5th edition book that I liked. And so those are them. If you have the 4th edition book, that's in the syllabus here. The 3rd edition book, did he send 3rd edition problems to anybody? No? Okay, so I can't help you with that. Pick problems and do them. That's all I care. Think about the same number of problems. You'll have a pretty good selection. Yeah, sorry. So then the next slide is this, and this is what I like to do with my slides. I put the first slide so you know it's my slides that have the homework problems that I picked. So yeah, this is chapter 14 problems. And because we're going to primarily be doing lab in lab from now on for a while, we're going to have to try to go through a lot of lecture notes. Okay, so I'll do my best not to be confusing on this stuff. Any questions besides where's the test and where's my homework?
The lab, the Monday lab today, are we having actual lab?
Yeah.
Both labs?
Yeah. Whatever I posted, if you look on Blackboard, I usually post, and it's on the syllabus, right? That's what I go by. And it's really what he originally posted was we're doing 2 labs this week. Okay, so we're going to do a little safety talk. The labs are pretty simple. The first one is a lot of, you're not doing anything hands-on. And the second one, what you're doing, was a little bit of hands-on. And the second one, what you're doing is you get 6 test tubes, and you put 5 known compounds in and 1 unknown. So you're going to get 1 unknown, okay? And then you run 3 different tests on it. And then the 3 different tests will tell you what your unknown is. But you're doing, right, 6 test tubes. First time you just look at the material and observe it. Second one you add water to see if it dissolves. Or the first one you do a pH. Second one you see if it dissolves in water. And third one you do an oxidation test. And then you identify the unknown. So think about how long that might take.
You must have not known it's the kickoff to fantasy football today.
Sorry. I did see the Fresno City College football game. I don't make very many of them, but I went to the one against Butte, Sierra. I think Sierra College. That was actually really good. It was Fresno City won in overtime by blocking an extra point.
Wow.
Yeah, so it was crazy. There was a lot of screaming. It's fun. And this weekend's the big game in San Francisco, so I'll probably go to that one if I don't have to go to one of my children's games. Okay. Right? Because I have a lot of kids, and we have soccer on Saturdays, and we have football games, and we have football games, and we have soccer games, football games, and more soccer games, football. All right. And volleyball hasn't started yet, so then eventually it'll be volleyball too. So we're going to talk about aldehydes and ketones, or carbonyls, and chiral molecules. Things that you have to be able to do is name and draw alkanes. So what I like to do with this slide is really quickly just do a couple of quick reviews. Okay. So let's say my alkane looked like, that's supposed to be connected. That's my alkane. How would I name that? What's the first thing that you do? Parent chain? Was that locked?
Yeah.
Good. Kick them out. I'm kidding. Hang on. Let me see if I can unlock it. It shouldn't be locked. Yeah, so the first thing that you'll want to do is you'll want to name the parent chain. So how many atoms in the parent chain? Okay, just give it to me later. So there's 6, right? So what is the parent? Hexane. So we can write hexane. Ooh, I wrote hexame. That's an N. All right. Okay. Now, second thing you have to do is you have to determine which direction to number it from, right? So the way I've numbered this, you can number it from the right, or the way I've drawn this, I can number from the right or I can number from the left. I'll choose the right. Why? Substituent gets the lower number, okay? So that means I number from this end. So I number 1, 2, 3, 4, 5, 6. Then what do I do? I identify the substituents and I give them their locants, their locations or their street addresses, whatever YouTube, you can watch all these things too. We call it whatever you like. So it's 2-chloro, 4-methyl, Those are my substituents. And then the name would be 2-chloro-4-methyl-hexane. Because you put the substituents in alphabetical order, right? And the parent goes last. Remember I told you when you go to Disneyland, parent always goes last. Good. Now, if I said I wanted you to draw 1 bromo, 2 chloro, 3 methyl. Remember, I have to make this up in my head. Hexane. What's the first thing you want to do when you're given a name like that? Draw the parent, right? So we draw the parent. And you should be getting better at drawing the parent, but that's a 6-sided. It looks like the honeycomb of a beehive, what it looks like. And then I just start 1, 2, and 3, because I have them like that. And in this case, I put the bromo here, the chloro here, and the methyl here. And whether or not you put the CH3 up there or you just leave it as a stick, it's fine. Okay? Now, alcohol naming, what's unique, what's different about naming alcohols than, let's say, an alkane like this? Let me give you a specific example. What's the difference when it's because the Cl has the lower number, right? What's the difference when you name alcohols, though? The alcohol, yeah, the OH is the parent. So it has to be on the longest chain. It gets the lowest number. Oh, and by the way, a lot of people, they get confused because I put Cl here, and they think it's another carbon, right? Because it's just C. Don't get into that trap, okay? So I'm going to number from this end, 1, 2, 3, 4, 5, 6. So this would be, just to make it quickly, it's 6 chloro. And then what? Hexanol, but not just hexanol, 2 hexanol, right? Because you got to tell people where the alcohol functional group is, because it could be on a number of different carbons. It could be on 1, 2, 3. Why couldn't it be on 4? Can you start numbering from the other end? Yeah, that's good. Yeah, just one of those trick questions. All right. Let's see. And just a quick reminder, reactions. Did I skip a slide? No, I didn't. Okay, good. Quick reminder, when we do oxidation, we're not doing the chemicals, not the reagents, but we're just using the symbol O to be oxidation. So if I have an alcohol like that, what kind of alcohol is that? Primary, secondary, or tertiary? Secondary. Well, you guys are really good at this, by the way. This is what I like about teaching 3B, by the way, because it's all the guys who could get through 3A. It's really nice. I mean, that's the same thing about OChem. But then you guys require a lot more, too, in some ways. But I like doing that. So we do oxidation, we do this, right? So we'll oxidize that. What do I get? A double bonded O, right? This functional group is what we're talking about today, actually. This is known as a carbonyl. And it's the basis of this chapter, ketones, aldehydes, ketones chapter, okay? What if it's a primary alcohol? What happens? And I go like this, and then I go like this. You know, like they do 2 oxidations. What happens? Get a carboxylic acid. And in the step in between, just so it's clear, it's an aldehyde, and then you do 1 more oxidation, and you put an OH down there, and that's 1 more oxidation. I actually think the whole slide is showing now. It is. Oh, that's nice. Okay, I complained about it. I guess somebody fixed it. Well, they have a lot of little background information. I'm going to skip some of it. But just so you know, formaldehyde is an important one to know. And there's a couple of common names when we do the nomenclature. The formaldehyde is the simplest of the aldehydes. It's shown over on the right, okay? And its systematic name is actually methanol, like methane, but ends in an AL, and I'll talk about the nomenclature. It's an important one to know because we use it for preserving a lot of biological specimens. It's also important to know is some people become allergic to it. And actually what it does, it binds to the proteins in your body and then causes an autoimmune response in some people. And the thing is, like, your body's really smart. It learns how to, like, respond to foreign invaders, right? Because your immune system is designed to protect you. And so what happens is, in some people, this response gets worse and worse and worse as they get more and more exposed to formaldehyde. Okay. So we're going to learn how to, in this chapter, identify carbonyls. Those are aldehydes and ketones. And then we're going to be able to write their formulas and name them and draw structures for them. Okay, so. Carbonyl group is an interesting group. It's this one that's shown on the top right. It's the C double bonded O. And what's the notation on there mean, the little squigglies? It's the dipole. And when you have a squiggly that looks like this, that's the negative side. And you have a squiggly looks like that, that's the positive side, right? So in a carbonyl group, you have an oxygen that's here and a carbon that's here. The oxygen's a lot more electronegative than the carbon, so it causes the molecule to have some polarity in this region, okay? Another interesting feature of carbonyls, which comes probably not into play so much this chapter, but comes into play in later chapters. Carbonyls are found in carboxylic acids. Carboxylic acids are found in, you know, biology. What are proteins made out of? Amino acids, okay? So a key feature of the carbonyl group is that it's trigonal planar. And in English, that means it's triangular shape and it's flat. Okay, it's a flat section of a molecule. The alpha helix that you see in proteins, the spirals that we see in proteins, the pitch in that spiral and the helices that you see in proteins is determined by the flatness of the molecule at that point. So proteins have these trigonal planar carbonyl groups all over them. And as a result, that determines, we'll talk about this later, but we'll talk about alpha helices, beta pleated sheets, and a lot of those structures are determined by the shape of this carbonyl group. Okay? So just remember, trigonal planar means it's flat, bond angle's 120, and it's polar. Okay. The other thing that contributes to the polarity of carbonyl groups is these guys. Okay. You have the more electronegative oxygen, but you also have the lone pairs on the oxygen, which make more negative charge on that side. So it's very strongly polar as a result of that. So when we talk about intermolecular forces, okay, which is what we'll be talking about here shortly, but we'll do the nomenclature first. But when you talk about intermolecular forces, how does increasing the intermolecular force increase attraction between molecules? If I make the intermolecular force stronger, molecules, they stick together more. They're harder to separate. That means like their boiling points, their freezing points, they all go up. Also, it helps them be dissoluble in water, and we'll talk about that when we get to that section. Okay. All right. So the book had this really complicated slide on naming it, and I really simplified it a lot. This was a page full of text. Okay. This is how you name. This is all you really need to know up here. So if you know the name, this is for aldehydes. Okay. And you know this is for aldehydes. Aldehydes all end in al, right? So aldehyde, al. all you do is replace A and E with Al. And of the functional group priorities, compared to, for example, alcohols, this is the highest functional group priority. So remember with the alcohol, when we named it, we had to make sure the OH was on the parent chain. Now it's the Al, the aldehyde, has to be on the parent chain. Okay, so that's what takes precedent. So if you have 2 carbons, by the way, that's the number 1 carbon, that's why I put that there. If you have 2 carbons, what alkane name has 2 carbons? Ethane, right? So it'd be ethane. So the name of the aldehyde would be ethanol. Now, aldehydes, we don't often, when you're naming an aldehyde, you don't often say 1-ethanol because it's always at the end, yeah? Since it's always at the end, you don't have to give it a number. People just assume it's at the end, okay? So there's some common names you need to know, and I would really rather not do common names, except that, why do we call them common names? Because they're really common, so you kind of have to know some of them, okay? So one of the things that you'll notice is what'll happen is these prefixes, that's these things here, okay, will be followed by aldehyde. So that's in the common name. So form, that's for 1 carbon, so form aldehyde. Some of these I can't even really pronounce. They don't like want to roll out the tongue. And then there's acetaldehyde. Okay, that's how you generate the names. Propion aldehyde, butyr aldehyde, valor aldehyde. If you know Roman numerals, the Roman numeral that helps, that's V, right? That's the valor aldehyde. That's 5 carbons. And then you can kind of fill in the rest with what you know. Capricorn is which symbol in the zodiac? I don't know that stuff very well. I think it's like the 6th month or something. But anyways, that's actually what this comes from. A lot of the compounds that come from 6-carbon carboxylic acids smell like goat. So that's where that comes from. Okay, so we'll move on. Just some examples of the systematic names. Methanol, ethanol, propanol, butanol, just like butane, and then you put Al at the end. Propane, you put Al at the end. One other one that you need to know is benzaldehyde, and that is really just benzene ring, right, with the aldehyde functional group attached. So that's benzaldehyde over here. Benzene ring with a aldehyde attached to it. And then I have a couple of slides if you want to download the slides that just tell you the rules for naming, but I'm going to show you how to do this without looking at the rules all the time. So let's go ahead and name this aldehyde. What's the first thing that you do? Parent chain, okay? So parent chain is like this, right? 1, 2, 3, 4, 5. And I'm going to start from this end because it's an aldehyde. That's the highest priority functional group. So I just put a 1 here. 1, 2, 3, 4, 5. That's the locant for the functional group, the 3. So 3 methyl. And then what? It's pentane, right? So pentanal, yeah. Yeah. And if you have more than one substituent, you put them in alphabetical order. Okay, so ketones. Ketones are different than aldehydes. Oh, I want to show you one other thing, actually. Sorry. Back up. There's a couple of ways to that aldehydes get drawn out. One is just this, C, H, and O. sometimes students get this confused with a different functional group, either a carboxylic acid or an alcohol, okay? Because they think OH, so it's a C with an OH. If you actually try to draw a C with an OH, though, this is what you get. And you can't get 4 bonds on the carbon, okay? The way this is written, with the H and the O like this, means that the H is attached directly to the carbon, and the O is attached directly to the carbon, okay? Can the O be directly attached to the hydrogen? Not if the hydrogen is at the going to be at the end, because we realize that you can't do this, okay? So people confuse this with carboxylic acids and alcohols all the time, so you have to be careful with that.
Do you have an alcohol or an OH like in the middle?
Yeah.
Would it be both?
No, because the number of, so, okay. The answer is no. Before I get all excited and give you something that's wrong. So if you had this, right, and then you condensed it down, it would be CH3, C, oh sorry, C, CHOH. Okay, the H directly on the carbon, and then the OH can't be attached to the hydrogen, has to be attached to the carbon. If you had the carbonyl group, so I have a CH3 here, and then it's C, and then I put a carbonyl there, it's C double bond O like that, right? I can't bond an H to it anymore. So the next thing that's over here is another C, right? So the way this is written as a condensed structure is CH3, CO, and then C, let's say this is CH2, CH2. Okay. So it takes a little bit of getting used to it. If you're not sure, just try drawing the Lewis structure for it when you get it and go, oh, it can't make those bonds, okay? But anytime in these structures, one of the things, anytime you have this hydrogen here in the condensed structure, it's attached to this carbon, and it can't be attached to this other thing because hydrogen can only be bonded one time. Okay. Okay, so ketones end in O-N-E. Okay. So you take in this case, this is this is 3 carbons, so it's propane, right? So you get rid of the E, and you put O-N-E. So propanone. And that's how you generate the name. It's just like the aldehyde. You just get rid of the last letter and add a new suffix to it. Why didn't I give a number? There's 3. It has to be in the middle. If I put it on the first one, it'd be an aldehyde, right? I don't have a different name. It turns out it's kind of funny. You don't need to use the number all the way up to 4. Because when you do 4, you end up with something that looks like this. Right? And that's butanone. It has to be on a number 2 carbon. If I put it on this carbon here, then I number it from the other end, and it's still right in the same number position. So for 1 through 4, they usually leave the number off where the ketone is, or not 1 to 4. From 3 and 4, they usually leave the number off. Okay, so some examples, right? Propanone, butanone. So you get rid of the E, and you add 1 in its place, right? And this is 3-pentanone, and that's to distinguish it, because now that you have 5 carbons, it could either be dead center, or it could be on this side, and this side, it would still be a ketone. So what would 2-pentanone look like? Like if I was drawing it, right, it's in this same style, it'd be CH3, and then depending on if I wanted to count from the left or the right, C double bond O, CH2, CH2, CH3. And this would be 2-pentanone. Okay? Any questions so far?
So, which one's the IUPAC name and which one's the?
Oh, so if I said this the other day, if it ends in the name of the functional group, it's a common name. So dimethyl ketone, right? That's the common name because it ends in ketone. But if it ends in a suffix like ONE or AL, then it's usually the systematic name. Okay. The common names for ketones are pretty easy to about probably they use common names to about 6 or 7 carbons. All you do is you name the alkyl groups on the left and the right of the ketone, right? And you put them in alphabetical order. So for example, that's why this one, the common name for this one is dimethyl ketone, because it's methyl and a methyl, there's 2 of them, right? And this is the ketone in the middle. This one would be ethyl and methyl, right? Ketone. Although in industry, they always call it methyl ethyl ketone. MEK is a very common solvent. Like if you're working in industry, they use it for, it dissolves like all kinds of crazy stuff. But in industry, you'll see this one abbreviated usually as M. Oh, sorry, not that one. This one's MEK. So methyl ethyl ketone, but typically we would say ethyl methyl ketone. And then this is diethyl ketone. And then once it gets really big, or if the side chains have any complexity to them at all, we don't use common names.
I was just wondering, 'cause didn't you say up till 4 that you didn't have to number it? On the-
Yeah, so this one's 5.
On 3 pendulum?
Oh, yeah, but this is, oh, sorry. 4 carbons in the structure.
Okay.
Yeah. Not 4 as the number. Yeah, 4 carbons in the structure. Okay, so let's, for cyclic ketones, can you have cyclic aldehydes? First of all, aldehyde's always at the end, and since it's cyclic, it can't, like, where's the end of a circle? You know, that thing that there was, the wedding band thing, and, you know, anyway, sorry. You notice I'm not wearing mine, but I am married, happily married 25 years. I told you the story about the iPads, right?
Yeah.
The silver iPads, yeah. So, and my wife works here too, so she keeps me in line. And I even allow her to track me on Find My Friends. I just figured it out. She's like, for the longest time, she says, if I can't track you, you can track me. Well, I don't know. And I figured out I have another device, and it's tracking that device, and that one's always at home. I'm home, honey. Oh, I didn't go out. No, I'm at home. So just like you would any cyclic, just like you would any cyclic compound, okay, you just name for the number of carbons, you prefix it with cyclo, and then get rid of the E and add O-N-E, okay? So cyclopentane, right? It's just pentane, right? But you have cyclo in front of it, it means it goes in a circle. Ketones are the exact same nomenclature. Now, maybe a little bit differently that we don't usually think about for cycloalkanes is because the carbonyl has a high functional group priority, it's usually always number 1. Okay? So it would be number 1 for cyclohexane for this compound. So this becomes 1, 2, and 3 over here. And it becomes 3-methylcyclohexanone. Rather than then saying 3-methyl or 1-methyl 3-cyclohexanone, that would not make any sense. So, and again, these are the rules if you want to have the rules somewhere. So let's name this ketone. Maybe I made these too easy. Sorry. Okay, pentane, right? Why did I do that? Because it's the parent. You guys all know this, I hope. If not, you'll practice and you will know it. I'm not saying you're all comfortable with it. I'm just saying you'll probably heard it once. That's pentane. So it's a ketone. So what do I do? Get rid of the E and make it 1. So then it says pentanone. And then you number from the side that gives the ketone the lowest number. And that means this is actually 2-pentanone. So the parent, 2-pentanone. And then I just have to decide what the substituents are. In this case, again, it's a methyl, but it could be anything. It could chlorine or bromine. So it'd be what? 4-methyl-2-pentanone.
You're always gonna number that carbon that has the O coming off of it.
Yeah. And it always gets the lowest possible number of the numbers that it could have, because you can number from either the right side or the left side. Yeah. And if it's an aldehyde, like if it's an aldehyde and a ketone, the aldehyde gets the lowest number, so that you don't have to, because it's on the number 1 carbon, so you always give it the lowest number. Okay? I'll do one example. They don't do much with it in the book, but I'll do one example so you can see it. So this would be 4-methyl-2-pentanone. So rather than rewrite this whole thing, I'm just going to be lazy.
But if it was butane or butanone, you wouldn't have to.
Yeah, if it was butanone, I could leave the number off. So if it was like this, I'd be 3-methylbutanone, because it could only be on the number 2 carbon. If you put it on this one, you couldn't have the methyl group there. Right, and so anyways, yeah, that's the idea. Just to give another slightly different example, your book does talk a little bit about this stuff, so it's maybe worth doing. So let's say I have this. They're both carbonyl groups, but because the aldehyde is always like at the end, it gets the number 1, regardless of where the other stuff is. Okay, because you want the first functional group to have the lowest number. So this is the 1, 2, 3, 4, 5, 6. So in the IUPAC system, you would name this as a aldehyde, and then you use a different name for the carbonyl as a substituent. Okay, so we're going to name it as an aldehyde, so it's pentanal. No number needed because it's on number 1.
Why not hexanal?
Well, that's exactly what I was just thinking when I looked at it. That's why they make erasers. So hexanal. Now on the number 5 carbon, that is now called oxo. So if it's a ketone and it's the parent chain is like using it for the parent chain, you call it oxo. You call it ONE. If it is a substituent, carbonyl as a substituent gets this oxo name. So this is a C double bond O as a substituent. So this becomes 5-oxo hexanal.
So if there's no other substituents, oxo.
Yeah. Well, because it's a carbonyl and you want it, that's a ketone, right?
Yeah.
But it's already, we're calling it an aldehyde. The parent is an aldehyde. So rather than saying Al and ONE at the end, they just call the carbonyl a substituent, just like a methyl group. Okay. Go ahead.
So if there's an aldehyde and a ketone, the aldehyde's always going to be.
Aldehyde's the parent. It gets number 1, and then you number everything else and name any other carbonyls as oxos.
Can you say again why you guys numbered it this way instead of the other way?
Oh yeah. Well, okay. So aldehyde's always at the end, right? So no matter what, it always is going to have a number 1. Ketones, the closest it can get to end is 2, right? So the aldehyde, remember the rule is you want to number the parent to be the lowest number possible, right? So that means the aldehyde is going to be the lowest number possible. It beats the ketone.
Can you have 2 ketones in aldehyde?
Yeah, and then they call it, 2 ketones and yeah, so let's say, okay, I won't ask you this, but that would be dioxo, and it would be 3,5-dioxo, yeah? If you want to become an organic chemist, then you can take the other class, and it actually takes us, check this out. It takes us 18 plus about 5 weeks. It takes us about 23 weeks to get to this point in the more advanced organic chemistry class. Yeah, it's in the second semester of 2 semesters of this. Right. Oh, sorry. So just so you see this is the list that the book gave, which you need to know. It gives the priorities, but you kind of know them now because of the way we talked about them. Halogens and alkanes are the lowest priorities, and they're always named as substituents. Then it becomes an alcohol, and then a ketone, and then an aldehyde. So, like I said, if it has an aldehyde functional group in it, then all of these things lose their priority and become substituents. If it has a ketone in it and no aldehyde, then all of these things lose their priority and become substituents. So when you have a ketone as a substituent, it becomes oxo. I'll show you how you do an aldehyde as well. But an alcohol becomes a hydroxy, like an OH is known as the hydroxy group. And then these are always going to be alkyl or halo, like chloro groups. So let me show you what a formal group looks like. Oh, shoot, what did I just do? No, I didn't mean to do that. I meant to do this. If I have a parent chain, and let's say I have that, so it's an aldehyde, right? And then over here, I have another aldehyde coming off. The longest chain is this one going across 1, 2, 3, 4, 5, 6. So this is just one carbon sticking off. This is the formal group that they're talking about. This guy, FORMYL.
So that would be 2. Or no, I'm sorry. You would start on the far right.
Yeah, start on the far right
Longest.
and go 1, 2, 3, 4, 5, 6.
But you would take 4 as like your.
Yeah, so it would be 4 formal hexanal. Yeah. You don't see that often. But carbonyls we're going to see a lot because they show up in sugars and all kinds of stuff. Okay, so that's why I'm trying to emphasize what's going to be important for you later in the chapters. By the way, did I tell you my grand plan for the final exams? Week 9, organic chemistry final exam. I told you that? That's the logical split.
Oh, yeah, separating.
Yeah. Huh?
Separating.
Yeah, separating it so you don't have so much to study. I mean, how would you like to not look at this stuff for like 9 weeks and then have a final on it? You'd be like, see you, Dr. K.
Are we gonna have like a week of review before?
If we can, but we're going to actually have a test the week before on the second half of the organic chemistry, and then you'll have the final for the organic chemistry. So you have 2 midterms and a final. So we'll have some review time for that second midterm, and then the final.
Do you know much from 3A for the exam?
No. Like what? Like partial pressure of hydrogen over water problem? No. I call them cow problems. You collect over water. So you take the first letter, COW. So I always tell students, you're going to have a cow on the final test. So they know what that means. It means to study that problem. And if you had me for 3A, do you remember me saying that? Saying you're going to have a cow. Anyways. All right, so just a couple examples of 2 functional groups. I'm not going to go into do a lot of naming on these. But you'll notice this is a ketone. Ketone has priority over alcohol. So this becomes 4-hydroxy-2-pentanone. Okay. Alcohol has, of course, priority over halide, so this becomes 2-chloro-1-propanol. And then the other one that's important to understand is this one. This is an aldehyde. Aldehyde has priority of the ketone, right? So you start numbering from the aldehyde, 1, 2, 3, 4. So it's 3-oxo, and then it's butanal. So that just follows the rules that we talked about earlier. Whoa, why is that slide in there again? I'm going to skip this stuff, but I left it in there. You can read it. Yeah, so some of the properties, we're a little bit on the properties, and then we have a whole section on properties. Some of the properties of aldehydes are actually they have a sweet smell. Not all of them do, but some of them do. So you guys are familiar with vanilla and cinnamon and almond, right? These are the smells of these different compounds. That's the odor that you get from those compounds is these particular compounds. Of course, if you smell straight vanillin, it doesn't quite smell like vanilla because there's other things in there. And usually vanilla is like 95% alcohol too, so you smell some of the alcohol that's in there, ethyl alcohol. But it turns out cinnamaldehyde, you can get it pretty pure and it smells like you want to eat it. It's really good. And I do like the vanillin. Vanillin makes me want to eat cookies. I don't know. Anyways. Okay, so we're going to do quickly a study check. What is that? We're going to identify these as aldehydes or ketones and then name them. And the naming we're going to do very quickly. I'm just going to write them out on the side, okay? Top one, aldehyde, 4 carbons. So what is it? Butanal. Okay. So this is an aldehyde and butanal. You don't normally see aldehydes drawn like this. Just telling you. I don't know why. This is a slide I stole from the book, so I don't know why they did that. What's this one? Got to be a ketone. Otherwise, there would be hydrogens here, right? But the double bond to the carbon takes the 4 bonds. It's how many carbons? 6, so that's hexanone. What else do I need? I need the 3. Because you could have a 2-hexanone. That would be the carbonyl group here. What's this?
Is B, is that also 3, or is that also propyl ethyl ketone?
Yeah, it would be propyl ethyl ketone. Ethyl propyl ketone, sorry, alphabetically, but yeah, you would figure that out. And like common names, I hate to tell people like common names, it's always going to be alphabetical because a lot of times it's not. That's one of the bad things about common names. They don't have a way of organizing the name, so it can be confusing sometimes. What's this one? Ketone. In a cyclic structure, has to be ketone. What gets the number 1? Cl, Br, or the carbonyl? Carbonyl. I made this one up to be confusing, by the way. So this is the number 1. Who gets, which way do I count number 2? What's that? Brome, towards the bromine is counting up. 2, 3, 4, 5. You notice if I went the other way, I'd get the chloro first, right? But because the B comes before the C, alphabetical, that's what determined the direction of counting on this one. So if you have a tie for which one could be 3, you go alphabetical and you number it that way. Okay? So this one would be 3 bromo 4 chloro. Cyclo, don't forget cyclo, yeah. 3 bromo 4 chloro. Cyclohexanone, cyclopentanone, sorry.
And which one is that one again? The ketone, aldehyde, or?
Oh, it's a ketone. And D? Aldehyde. Numbering from the right, 1, 2, 3, 4. I actually think we did this one earlier, but it's going to be 3 chloro, and then butanal. Like that. Good? Yay! I'm not sure what I meant to do with these. I think I just was going to show all the work here and then decided not to. So now, a couple more nomenclatures, okay? IUPAC name for these. A is, oh, actually, did I make a slide for it? No, I didn't. Good. A is, what's the parent? pentane, so pentanone, right? Or pentanal, sorry. And then you number from the CHO, so this is 1, 2, 3, 4, 5. So it's 4-chloro.
Can you explain the difference again between CHO and COH?
CHO is the way people normally do it. COH is just a variant. It's just they put them in different order.
But it's the same.
Yeah. The way I learned it, honestly, and I learned this like when I was in college, it was a while ago. Rancho aldehyde. Rancho, like a rancho, like a ranchero or rancho aldehyde. And then it stuck with me. CHO is the way you always write aldehydes. But unfortunately, this book sometimes writes COH, and I'm like, I've never seen that anywhere else really commonly. So, okay, what's B? What's the parent for that? It's close. It's benzaldehyde. Okay, so this is one of the ones you have to know that the parent is that. And then you have to know benzaldehyde. So it's actually 2. Oh, and this is the number 1 carbon. So this is 2-ethyl benzaldehyde. Oh, I don't need that hyphen in the middle. Oh, darn. Okay. So make sure you know benzaldehyde as a structure. One more practice is a ketone. What would the parent be? Oops, sorry, I didn't mean to do that. Cyclo, don't forget the cyclo. And then pentanone. And then you start 1, 2, 3. So 3-ethyl. Okay, cyclopentanone. Good. So we're going to move to the next set of slides. That covers section 1 of the book. I'm going to basically knock these things off in order. I apologize for the density of material. Let's take a quick preview of what we're talking about here. Yeah, this is a short section. Okay, so one of the things about aldehydes, they're very polar, and in their interactions, or ketones, they're very polar, and in their interactions with water, remember water can hydrogen bond. Aldehydes and ketones, that oxygen has lone pairs of electrons on it. And so water can actually hydrogen bond an aldehyde, which helps to increase its solubility in water. Okay. The other thing, though, even without water, because ketones and aldehydes are so polar, they have relatively high intermolecular forces. Not like water or ammonia or things like that, but relatively high dipoles. Okay. So just to give you some idea of how that intermolecular force affects carbonyls, here's 4 different compounds, right? Butane, propanal, propanone, and then propanol. So propanol is what kind of functional group? It's an alcohol, right? And all alcohols can hydrogen bond, okay? So alcohols are hydrogen bonding because they have that group on it. And one of the things that you get taught about hydrogen bonding in terms of intermolecular forces, it's very strong, okay? So what they did is they took 4 different compounds, all that have about the same molecular weight, so they're all 58, okay? And then you have alkanes, aldehydes, ketones, and alcohols. And you'll notice what happens to the boiling point. For butane, the boiling point, that's like a butane, like in a butane lighter. Have you ever seen it? It's actually filled with a liquid because it's pressurized. If you break it, it's kind of fun to. Have you ever done that? Take a hammer, and you don't do this in a closed space in case you ignite it. Which, of course, when you're young and you're unsupervised, let's put it that way, like I was sometimes, you just did these things. When you take a hammer and you break a butane lighter, and the liquid comes out and it boils instantly, and it's flammable. So, but you can see that liquid. It's very at if it's 0 degrees Celsius though, and you try to light a butane lighter, anybody know what happens? You can't light it. So like when skiers go skiing, if you keep like a lighter in the outer pocket and you go to light something with it, it won't light because it's too cold. So what do they always do? They take the lighter and they stick it in their inner vest pocket. Then your body heat keeps the lighter hot enough that when you go to light it, it's actually above its boiling point and you can get butane out of it. Anyways, propanol has a boiling point of 49, propanone 56. The subtle difference here can be explained, but I don't think we need to know the explanation for that in this class. And then propanol has a boiling point of 97 degrees Celsius, so it's a lot higher. And the whole idea is carbonyl groups, right, very polar, and as polar carbonyl groups line up with each other, that intermolecular force of attraction holds them together. Their boiling points are higher than just a straight alkane, but lower than the alcohol that has the hydrogen bonding, okay? So it turns out at room temperature being about 25 degrees Celsius, arbitrarily, methanol, that's formaldehyde, and ethanol are gases, acetaldehyde. 3 to 10 carbons, though, are all liquids, and then beyond that, they become solids. Okay? Aldehydes and ketones have higher boiling points than alkanes of similar mass. These are the things that you have to remember, okay? And lower boiling points than alcohols. And that's because they don't hydrogen bond. Okay? They're polar but not hydrogen bonding. So the way these chapters break out, I don't know if you've noticed so far, we usually talk about the names and how to draw them and that kind of stuff. And then the second thing is physical properties. We start talking about their boiling points. And the third thing that we usually hit is their solubility, is how do they interact with water. Okay, so the next thing, if you want to keep a logical list of what we analyze in each chapter, okay. Solubility of aldehydes and ketones basically follows that of alcohols. 1 to 4 carbons, soluble in water. Okay, so if you have an aldehyde, like, you know, when you go to biology, right, and you have a formaldehyde solution, it's actually just a few, it's like 15 or 20% formaldehyde in water. It's a solution of formaldehyde. Otherwise, the formaldehyde is a gas, okay? 5 or more carbons are not very soluble in water. And the solubility that they do have is attributed to hydrogen bonding with water between the oxygen of the carbonyl and the hydrogen of a water molecule. So this is what I talked about in that previous slide. Okay. Where do you guys encounter acetone? Yeah, nail polish remover, yeah. Your body tolerates it pretty well. So you know where formaldehyde, I don't know where you would encounter ethanol actually, or acetaldehyde. I use it in chemistry a lot, but I don't know what. Yeah, anyways. So just to give you some examples, this is like a gigantic chart, so it's a little bit hard to look at. But methanol, ethanol, so these are all aldehydes. This is aldehyde. So this is 1, 2, and 3 carbon aldehydes. You notice the boiling point goes up as the aldehyde gets heavier, okay? And usually boiling points tend to go up with molecular weight. They all have the same functional group. And then you have 3 carbon ketone, 4 carbon ketone, right? And you look at these, again, the number of carbons partially determines what the boiling point. So molecular weight goes up, the boiling point goes up. All of these from 4 and down are soluble in water. which means you can just mix them and they'll dissolve, right? Once you get to 5, then we get to slightly soluble, and once you get to 6, then it becomes not soluble at all. Okay? Now, it's still a liquid, okay, but it behaves like oil does, and when you take oil and water, what happens? They separate, right? Which one goes on top? Oil. Why does it go on top? Less dense, right? So the same thing happens with these longer chain aldehydes and ketones. When you go to mix it with water, it behaves just like oil does with water. You could shake it up all you want and then set it to the side, and then they end up separating into 2 layers, okay? Did you guys learn about in Chem 3A about emulsifiers?
You're talking about like, well, it's more like
Bio, yeah. So like when you make a Caesar salad, you guys know what an emulsifier is? Yeah, it's got properties of the oil and the water, so it's got long carbon chains to it. It also has nitrogen positive groups in it, so that helps it attach to the water, while it also helps the long hydrocarbon binds with the oil. Yeah, it's like soap is kind of an emulsifier, so that's how soaps clean things. You can get these things to mix if you use an emulsifier. But what's the most common emulsifier, like around your house? Besides soap. What? Yeah, bile's an emulsifier too, but you don't want to use that. Hey, I'm going to make Caesar salad. Just a second. You know how hard you would have to throw up for that to happen? Oh, yeah, because it has to come out of your bile duct, which is past your stomach. Well, just have a big blockage first, and then it'll all come up to kind of black, gassy looking stuff.
is it green?
Well, I've seen people throw it up before, and when it comes out, it's black. So that's when it's dried onto something. So, yeah, I don't know what it looks like. I wasn't there when it happened.
Okay.
Yeah, but yeah, it's emulsifier. So, egg whites. Egg whites have lecithin in them, and lecithin's it's emulsifier. You can use that if you want to get oil. If you wanted to get it to blend a little better, you just put a little egg white in there. Or you can buy just lecithin and shake it together. Okay, sorry, that was a little aside, but I thought you might find it interesting. So we're going to do a study check here. Which of those of A will have a higher boiling point and why? I heard alcohol. Right? The alcohol will have a higher boiling point because hydrogen bonding. B, which one? Oh, sorry. The ketone. Why the ketone? Dipole. Yeah, it's polar. Alkanes are nonpolar. And C? Ketone. It's almost exactly the same question as the one above. It's alkane versus a ketone, but it's dipole interactions again. Good. So now this is the is it soluble in water question, right? A, soluble, not soluble? What's that? Not soluble. You know why? It doesn't have any functional group on it. Alkanes are not soluble in water. You can get some gases dissolved, like some methane gas to dissolve in water, but that's a different thing. But like making a solution, well, you can't get it to go. What about B? Soluble. C? Not soluble because of 5, and it's a carbonyl.
Could it be slightly?
It would be slightly soluble, yeah, exactly. And in our book of random chemistry knowledge, slightly soluble is not really soluble. It's slightly soluble. Does that mean it's like, is there partial credit? No. So, and the bottom one? Soluble. So B and D are soluble. C is slightly soluble, and A is not soluble. Just it's alkane. All right. Well, that's that section. Next. That was a short one. You know what we're going to do? Let's take a 5-minute break in the middle of lecture, because I'm going to get some water and wash out my cup because I'm thirsty. And then we're going to start section 3, and then we can, after that, we'll cruise and we'll do 4 and 5 in the next lecture. But 5 is kind of a bear, so you might want to look at that one ahead of time. So let me take it. Okay, so reactions of aldehydes and ketones. One of them is called Tollens test. The full name of it's Tollens silver mirror test. And in this silver mirror test, you actually see they have a picture of it on the right here. You take an aldehyde and you react it to form a carboxylic acid. So the aldehyde's getting oxidized, okay? Now, if you remember from Chem 3A, when you have an oxidation reaction, you have to have a reduction reaction. The reduction reaction that they pair this with or couple this with is the reduction of silver ion to silver metal. And the reason it's called the silver mirror test is because it literally looks like a silver. Produces an old-fashioned silver mirror surface. When you, maybe we'll do this when we get close to Christmas. I always have this weakness, and one of the things I like to do is make Christmas ornaments. This is how the old-fashioned Christmas ornaments were made. You take a glass bulb, you clean it out really well on the inside, and you take the silver solution and you add a little bit of the aldehyde we usually use is glucose. Add a little glucose to it, and it plates silver all over the inside. And I've had some of these that I've made like 15, 20 years ago, and they're still bright and silver on the inside. So it's a fun way to do it. But the idea is this. In Tollens test, you're taking an aldehyde, converting it to carboxylic acid. That's an oxidation reaction that we learned from last chapter. And at the same time, when that happens, you have to reduce something. In this case, we use silver as the metal, and that produces silver ion and produce silver metal, okay? So, Tollens test is one of the tests that's used to distinguish between aldehydes and ketones. Because you're converting it to a carboxylic acid, if you remember from that last chapter that we covered, because you're converting it to a carboxylic acid like this, okay, there has to be a hydrogen here for you to oxidize it. When you look at a ketone, right, there's carbons on either end, so you can't oxidize that any further. And so this is what they say is no reaction. But for a Tollens test, what that means is you don't get the silver mirror. Okay. All right. Benedict's test is another interesting test. It's for beta hydroxy aldehydes. So what does beta hydroxy mean? Hydroxy is an OH group, okay? Anybody know the Greek alphabet? What's the first one? Alpha. And then beta, gamma, delta, A, B, C, D, delta, epsilon. Okay. If you have this is a little bit of old nomenclature stuff that crops up. Here's your functional group, right? This is alpha. It's the first one, okay? Oh, I'm sorry. It should be an alpha hydroxy aldehyde. I think I read beta somewhere. I'll have to double check that. But the idea is if you put an OH here, okay, you need to have that OH for this Benedict's test. Simple aldehydes, like if the OH wasn't here, okay, wouldn't oxidize in this test. But it's the same, it looks just like Tollens test, right? If you ignore this part, and you have aldehyde go to carboxylic acid, looks just like Tollens test. The thing is if you don't have this OH test, then Benedict's test doesn't work. So what is Benedict's test? Well, it's an oxidation reaction. You have a reduction, and what you do is you reduce copper, okay, 2+, to copper 1. This is Cu plus 1. And it turns like this copper 1 oxide is red. So you start with this blue solution, you mix in your compound. If it turns red, you know you have an aldehyde with an alcohol functional group next to it. Okay? So you're like, and? Like, why do I learn this? Okay, it turns out this kind of functional group arrangement is what we find a lot in sugars. So like glucose, any of the aldehyde sugars, glucose, let's see, what's that? Maltose? No, maltose is a disaccharide.
Okay.
But for the simple sugars, you find this aldehyde functional group at the end with an OH group next to it. So in the old days when people had sugar like in their urine, there were a couple of different ways they tested it. Right? One was they drank it. And if it, right, I know, we don't do that anymore.
We're really like killing it today with all these.
Weird ideas, yeah, sorry. It's true though.
It is.
I used to be so grossed out because I would go to the doctor when I was a kid. And one time I saw him standing back there, he took my pee and he put it on his finger and went like that. And I don't think he wanted me to see that, but that's a test for diabetes. One of the reasons that, one of the ways people with diabetes back in the Roman days were people were able to tell that they had diabetes is because the flies would always gather around their feet because of all the sugar that was in their urine. You know, you went pee and it got it on your feet, and then that sugar on your feet would attract bugs, and they would always have bugs around their feet. Anyway, sorry. The other way is this Benedict's test, right? So what would you rather do, have Benedict's test or drink pee? I mean, sorry. Went a long way for that joke. So 2-hydroxypropanol, right? Copper 2+ from Benedict's reagent, and this is the brick red copper. So this is the part that gets reduced, and this is the part that gets oxidized over here. So there's a little side note. You know, sugars like glucose contain this kind of aldehyde functional group. You can detect glucose in urine or any fluid sample using this test.
We used to do micro, actually.
For
It was like, I'm sorry.
probably a sugar test.
Yeah, to test for sugar.
Oh, did you use it for amylose? Did you use amylose and then a starch and
Yeah.
produce glucose? And yeah, because amylose is a polymer of glucose, and you amylose anyway. We're actually going to do that later. So. It's some of the little bit of biochemistry I can't remember. All right, now. I think I screwed this slide up. I meant to do something else with it. So let me make a new blank slide. And I'm going to do this because I like the way it looks better. So that was the oxidation of aldehydes. You can also reduce aldehydes. So if you do a reduction of an aldehyde, okay, what do you get? You guys remember?
Primary.
Huh?
Primary alcohol.
Primary alcohol. Very nice. And like I said, when we were covering stuff, it's essentially you're adding hydrogens. That's a reduction reaction. Okay. If you increase the bonds to oxygen, that's an oxidation reaction. And if you add hydrogen, it's a reduction reaction. One of the things I'm not sure how much you need to know, and this is where I was talking about earlier, your book does mention that the compound that's used for this is this guy. And he has a name. It's called sodium. And this is known as borohydride. Sodium borohydride, if you want to think about it, is boron with a bunch of hydrogens attached to it like this. Okay. Single bonded. How many bonds does boron normally make? If you look on the periodic table and you look for boron, what group is it in? 3, so it usually makes 3 bonds, right? In borohydride, it's made a 4th bond because it's picked up an extra electron. Okay, and that's what it turns out, it has a negative charge. So sodium borohydride is this. So that's the longest side. Sodium borohydride, NaBH4, is used is the reagent that is typically used for reducing aldehydes to primary alcohols and ketones as well. So ketones, when you do a reduction, right, you're going to add hydrogens. So you get this and this. So you get a secondary alcohol. Okay. So sodium borohydride will do either of those transformations. What I'm not sure is if you need to know sodium borohydride or just R.
So how do you know what's going to be on the right side? Because on that one, you added 2 H's. Like, how did you know to add 2 H's?
Well, I added 2 H's. I added a bond to this one and this one, right? Here, there's already a hydrogen here. So ignoring that one, I added 1 hydrogen here and 1 hydrogen here. It's exactly the same thing.
So for that one, you just added a hydrogen, or both of them you just added hydrogen? Or?
Yeah, hydrogen on each side. Yeah. So whereas this oxygen doesn't have any hydrogens on it and this carbon has 1, when I'm done, this one has 1 and this one has 2. So I added 2 hydrogens to that one. And then on this other one, I had 2, right? I had no hydrogens here and no hydrogens here, but here I had 1 and 1, so I added 2 hydrogens to this one as well. Okay. The other thing that your book mentions, which is actually on the slide, the same reaction can be done with this. The way it's phrased, let me go back to the previous slide. The way it's phrased is hydrogen, oh darn, hang on. Hydrogen, it's kind of confusing. I just took this from the book's slides. Hydrogen and a metal catalyst. So nickel, palladium, platinum, and hydrogen can be used to do the same reduction reaction. And ignore this down here because I was supposed to get rid of that. Okay. So if you want to take aldehyde or ketone and produce the corresponding alcohol, this one would be a primary alcohol, and this one would be a secondary alcohol. You have a bunch of things that you can do, and the list of them is a little confusing. It's hydrogen and one of these metal catalysts that's down here, or you could just use sodium borohydride. Okay.
But those are solid, so how would you react?
Yeah, so usually, yeah, nickel, platinum, and palladium are all solid. So the reaction can be a little bit slow. So what they usually do is they basically, they don't grind it, but think about it like they grind it up so the particles of the metal are so small that they have a huge surface area. Okay? And in fact, the particles for these are so small, they're not shiny anymore, they're black. They don't reflect light anymore, they're so small. Okay, good.